All right, let's finish our discussion of calorimetry with tidying up a few of the last-minute details around this topic. I want to finish with solution calorimetry because that's an expansion of what we've talked about so far that'll allow me to explore some of the other perhaps esoteric details of how we think about energy changes in reactions. Okay, so let's go through a whole bunch of, topics that will ultimately allow us to calculate some enthalpy changes within a solution calorimeter. So why is that different? Why do we need to worry about anything beyond what we've done so far? Well, really, we're not going to worry about much beyond what we've done so far because really the most important thing in calorimetry is the first law, right? The first law of thermodynamics is what allows us to say that the energy change or the heat energy change associated with the system is equal to the exact opposite as the heat energy change associated with the surroundings, right? This is the important piece. And we use this to determine the enthalpy change for any particular process. And the bomb calorimeter was, our first foray into actually doing this. But there are all kinds of other types of chemical reactions. We don't need to just worry about combustion reactions. There's a whole plethora of them. And we'd be interested in understanding what the enthalpy change is for all of them. So there are some things that you need to know in order to wrap your head around how to do that in all of those different contexts. So first and foremost, we have some terminology, some symbols, if you will, that we use to describe these processes. So delta H is sort of the obvious. We already know that delta H, insofar as we've defined it, is equal to the heat change for a constant pressure system, right? Or so this is how we defined it so far. But as we said, there's all kinds of different types of reactions. In the last lecture, we defined specifically delta H for combustion, for example. And so we used a subscript of combustion. But there are all different kinds of energy changes. We've talked about phase changes so far in this class. We talked about the energy change associated with melting. We talked about the energy change associated with boiling, which was vaporization. And in melting, that particular case, we talked about fusion, right? Fusion is the word that we would use. So the enthalpy of fusion, it corresponds to how much enthalpy we need to melt something. And so this is common to see different subscripts on all these different types. And there are many, right? So there are formation enthalpies, which we'll talk about a little bit later on today. That's a special type of reaction. Obviously, combustion, we mentioned vaporization, right? You name the process and you can define an enthalpy change for it. But fundamentally, that change in enthalpy, they're all the same physical quantity, which is the change in heat energy from an initial state to a final state. Now, you'll see different subscripts. Sometimes in some textbooks, you will see those subscripts shifted slightly. So sometimes we write them there between the delta sign and the H sign, or the H letter. But again, nothing different in this context. This is really just the same exact quantity. It's still equal to the heat change for a constant pressure process. No different there whatsoever. It's still equal to the mass times the specific heat capacity times the change in temperature. Again, no difference there. That's how this works universally. But the symbols are sometimes different. Now, also, there is another sometimes subtle change, and in particular with the formation enthalpies. These are often written with circles, these little circles up in the top right-hand corner. Now I'm going to move this over just so we can deal with it specifically. In this particular case, these circles actually have a specific meaning. So this means that these values, or whatever, if this was in a table somewhere and you had delta H written with a little circle above it, what this really signifies is the conditions that this number was measured or calculated under. So these are called standard conditions. So you'll often hear the phrase, standard enthalpy of formation, or standard enthalpy of fusion, or standard enthalpy of whatever else. If possible. And under those conditions, what we're saying here is that these enthalpies were measured under standard conditions. And so what are standard conditions? I mean, the reason why we do this is because you know that the energy change of a particular chemical process depends on a whole host of factors, things like the concentrations, the pressures, right, the temperatures. All of these things can change the amount of heat energy required or given off in a particular chemical process. So it makes a lot of sense for us all to just essentially agree on a series of standard conditions so that we can all list these in tables for whatever process we need. Now, we're going to use data like that exists in tables in the not too distant future. And so it's important. We need to know that, oh, okay, this was collected under standard conditions. If I'm not interested in standard conditions, then I can take this number and maybe do something with it and translate it into, whatever conditions I am interested in. So it's important to have. And what it actually means I suppose in literal form is a series of different things depending on what substance it is that you're talking about, right? So for pure substances, we're talking about the standard state of a pure substance, and that's your most stable state. So whatever your most stable state is at 1 bar, so a pressure of 1 bar, that is what is known as your standard state if you're a pure substance. So for example, if you're oxygen, O2, your standard state is the gas state, right? Because at 1 bar, you're going to be in the gas phase. Now, if you are a gas, so let's continue to talk about that. Your standard conditions is 1 bar of pressure. So the standard state or the standard conditions for a gas sample is 1 bar of pressure, because obviously this could change. It could be different for different conditions. And if you're an aqueous substance, right, so if you're in solution, which is something we're going to talk a bit more about today, your standard state, if you will, corresponds to a concentration of 1 molar, right? So 1 molar. And we'll talk about concentrations, of course, later on today, but molar, given the symbol uppercase M, corresponds to moles per liter. So how many moles of this thing, this solute, do you have per liter of total solution? And so that's what we define as the standard state. And so if we're talking about standard conditions of a particular reaction, this tells us a lot about the conditions that the various reagents were in when we performed this reaction. Now, generally, we think about temperature as well. We think about temperature as being 25 degrees as part of the standard conditions, but that's not always the case. There are such things as standard heats or standard enthalpies at different temperatures, but all other things considered equal, it's likely that 25 degrees Celsius is the conditions for any measured enthalpy change where you see standard conditions indicated. So those are the conditions. And specifically, if we're talking about formation reactions, which isn't necessarily the focus for today, but that's what we've been picking on so far, this little subscript of an F here indicates that this is an enthalpy change for a formation reaction. If you're wondering what that actually is, a formation reaction is one in which we form exactly 1 mole of our product. Right? So that's why we call it formation reaction. We are forming something. So the formation reaction for, say, ethanol, so the formation reaction of, say, ethanol is a reaction where we're going to form exactly 1 mole of ethanol from pure elements in their standard state. So ethanol has carbon, hydrogen, and oxygen in it. So we'd be asking ourselves, what is the standard state of pure carbon? Well, that's graphite. What is the standard state of pure oxygen? Well, that's gas. We know that, O2 gas. What is the standard state of pure hydrogen? Same thing, H2 gas. So if I can create ethanol from those 3 things in their standard states, that is precisely what a formation reaction is. Now, we're going to use formation reactions in a future class, so it's important to define them, but we'll come back to that later. So let's try a quick problem. I'm going to do the one that we've listed in the notes, and it's just a solution calorimetry problem. So we're talking about a reaction, and specifically what we're talking about in this problem. So let's define some of the parameters of this problem. We're going to have 50 mils, so 50 milliliters of a certain concentration, so 0.100 molar silver nitrate. So that's AgNO3. Okay, so we've got some aqueous silver nitrate, and we've got 50 mils of it. We're going to react that with another 50 mils of a different solution. So it's going to be also 0.1 molar, but it's going to be hydrochloric acid, so some HCl. All right. Now suppose we mix those two solutions in a calorimeter. All right. So an instrument that is meant to be mostly insulated, and this reaction is going to cause a temperature change, and really we're just going to measure that temperature change, right? That's what solution calorimetry is. Same fundamental principle. The reaction will cause a temperature change, and we're going to measure that, just occurring under different conditions. This is no longer bomb conditions. This is solution conditions. So we've got a couple of solutions here. We're going to mix those and see what happens. Now suppose the temperature initially, before this reaction happened, was measured to be 22.30 degrees Celsius. All right. Now our final temperature, suppose the reaction happened and the temperature increased a little bit and we went to 23.11 degrees Celsius. And so there we go. We've done this reaction inside a calorimeter, and we've noticed the temperature change, temperature's gone up. And what we want to know is what is the enthalpy change for this particular reaction. That's what we want to try to figure out. So we would need to be told a couple of other pieces of information. So we would need to be told either what the mass of this solution actually is, or we would need to be told maybe what the density of this solution is. How many grams per milliliter of this solution do we have? Right? We can see we've got 100 milliliters. Either one would allow us to determine the total mass of this particular sample. So let's just say we know that the total mass is precisely 100.0 grams, right? Okay, so this is the mass of our solution, which we could have calculated if we were told that the density was 1 gram per milliliter, right? If we knew that the density was 1 gram for every milliliter, we can see that we've got 100.0 milliliters, so we know we'd have 100.0 grams. So either way would be sufficient. We'd also need to be told what the heat capacity of either the calorimeter or of the solution actually is. And so in this particular case, we're going to be told that it's just going to be that of water. So the heat capacity of water is, as you saw in a previous lecture, 4.18 joules per gram per degree Celsius. All right, so again, as with all heat capacities, this tells us precisely how much energy we need to raise a gram of this substance by a degree. So we are essentially ready to go here. As we know, the heat change of the reaction is going to be exactly the opposite of the heat change of the solution, right? That's just the first law of thermodynamics. And so what is the heat change of the solution? Well, the heat change of the solution is just the mass of the solution times the heat capacity of the solution times the change in temperature. Right? So MC delta T. We've seen this many times so far. Now, in this particular case, we're told what the mass is. The mass is 100 grams. We're also told what the heat capacity is. I'm going to fix my 1 here because that doesn't look very clear. Let's just erase this border here. 100, there we go. So we're told what the heat capacity is. We're told it's 4.18 joules per gram per degree Celsius. Now I can already see before I go any further that grams will cancel with grams there. And my heat change, of course. Now, if I look at my heat change up here, it's going to be, as all deltas are, final minus initial, 23.11 minus 22.30. By my math, I get 0.81 on that. So the temperature change is 0.81 degrees Celsius. And maybe just a quick thing I would point out here, which is sort of interesting, is notice that we've actually lost significant figures here, right? So if you're not tracking significant figures, this is an opportunity for you to go wrong. Because if we look at all of our data, right, this is a calculated piece of data. But if I look at this and this and this and this and this and everything, they've all got 3 or more significant figures. So when I dump all my numbers down in my math and I ended up working it out, it's tempting to just use 3 significant figures at the end of the day. But that would be erroneous because we can see right here, these 2 numbers, if I take the difference, they turn into this. And this only has 2 significant figures. So this drastically impacts the number that we get. Okay, so I'm flagging that as something to pay attention to. And so I can fill it in now, 0.81 degrees Celsius There we go. And so this is how I would calculate the heat change for this particular reaction. So plugging all of those numbers in, I think you'll find that we calculate that to be 338.58 joules, which of course rounded to two significant figures, which I should do because of this number, gives me an even 340 joules. So that's my energy change. And again, I should be a little bit more explicit here. My Celsius will cancel as well, and that's why I'm left with joules. So my final answer here, 340 joules is the output of this reaction, and actually, I've made a small mistake here if I go back through and account for that. My negative sign, right? So I should be carrying my negative sign all the way through. And so this is an exothermic reaction at a value of 340 joules. This is an exothermic 340 joule reaction. Now that makes sense because I look and I see my temperature increased. Right? My temperature increased. So the Q of my solution went up, right? But that's why it's got a negative sign because my reaction must have given off that energy. If the solution's temperature went up, it's the reaction that's giving it that energy, right? So the reaction loses the energy and the solution gains it. And so that's why we call this an exothermic reaction. Now, what if I wanted to express this in terms of moles, right? In terms of joules per mole. This is a common way to express our energy changes. And so let's consider how to do that. What I'm going to do is move some of these quantities up and out of the way a little bit and carve out just a small little bit of space down here. So if I want to know about moles, the thing I need to do is I need to find out how many moles actually reacted in this particular case. And I can see up here that I've got volumes and concentrations. It's a very common scenario. You'll see it all the time this semester and next. You've got a volume of a particular solution that has a particular concentration. So what we're going to do is we're going to extract moles from that because we know that 0.100 molar, capital M, really means moles per liter, right? And so do I have a liter? No, I don't have a liter. I actually only have 50 mils. But 50 milliliters is 0.050 liters, right? And technically, I guess if I'm being really nitpicky with my significant figures, I should put an extra zero there because I do know it that accurately. And so if I multiply these two, right, this is my concentration times how much I actually have, what I get here is now two zeros. And if I'm going to be, again, nitpicky with my significant figures, I can keep going. That's moles, right? So 0.005 moles is what I have. So if I'd like to know what is my energy change per mole, I just take my 340. So I take my minus 340 joules and divide it by the number of moles that I actually have. And I'm only going to keep two significant figures there because my numerator is only to two significant figures. And so minus 340 over 0.005 gives me my minus 68,000 joules per mole, which, as we all know, 1,000 joules is a kilojoule. So this is exactly the same as saying minus 68 kilojoules per mole. And that's my enthalpy change for this particular reaction. Now, why didn't I use the HCl? Well, I could have. I could have used the HCl. This is a sort of a special case. Notice that the volume and the concentration are both identical for both of these species. So if I say, hey, how many kilojoules per mole? In this case, I didn't have to specify which of the two because they were both identical. But in principle, it is really important to specify which one you're worried about, right? Per mole of what? That's an important question to answer. If I say, hey, what is the enthalpy change of the reaction per mole? Strictly speaking, I should be saying per mole of, silver nitrate or per mole of hydrogen chloride. I should be saying which one in particular because in principle, it could be different, right? I could have different numbers of moles of each of these things. Now, it would become important to understand what the limiting reagent was if I had different numbers of moles here, but it really depends on not only which one of these is limiting, but what is the reaction stoichiometry? Okay, now in this class, we haven't talked about limiting reagents or reaction stoichiometry at all. So if that sounds confusing to you, don't worry about it. We haven't gotten there yet. But for those of you who are maybe wondering, why did I pick silver nitrate? Well, in principle, it didn't matter which one I picked, but it does matter generally speaking. And so I just want to be clear about that. All right, so this is basically it, right? We take account of all of our heat changes. We use the first law to come up with this relationship here. And my delta H is, of course, equal to my heat change, which I worked out to be minus 340 joules. But I wanted to express that as per mole, so I worked out how many moles I had, and there we go. And so my other final answer, I suppose, in the other unit system is simply that. And now I think you have all the tools you need to work out calorimetry problems involving first law and heat changes. And what we're going to do now is, now that we have an understanding of heat changes and delta H's, we are going to use those next week to be able to calculate heat changes for really any theoretical process in the universe. Really, really powerful technique. It's going to be interesting. So I look forward to chatting with you then.